Hi everyone, my name is Rika and I'll be one of your Chem 3B and 3BL GSIs this summer. I thought it might be helpful to make a quick review video for NMR, as you'll be seeing it in every lab for this course. For HNMR, we look at four main aspects. There's labels, integrals, chemical shift, and multiplicity. Labels, as indicated in the blue, tells us how many different kinds of protons or hydrogens there are. In this example molecule, there are 7 different kinds of protons, and they are labeled proton A through proton G. For integrals, this tells us how many of a given proton we have. In this NMR spectrum, I've underlined this integral in pink. Chemical shift gives us the position on the x-axis of an NMR spectrum, and it tells us the electronic environment of a proton. The units of a chemical shift is ppm, or parts per million. And finally, we have multiplicity, which tells us how many neighbors a given proton has, and that corresponds to the peak shapes of each signal. When analyzing an NMR, a table like this can be really helpful. We're going to try to identify which of these signals correspond to which of these protons, and we'll take it step by filling in this chart. So the molecule has already been labeled, so the label column should be easy. We have labels A through G, so we're going to go ahead and write that down into the chart. So A, B, C, D, E, F, and G. Then we have the integrals. The integrals asks, how many of each proton do we have? So I'm going to go ahead and write in all the hydrogens so we can count them easier. Now that all the hydrogens are written in, all we have to do is count them. So for label A, we can see that we have 3 hydrogens. So for label A, the integral is 3. For label B, we see that we have 2 hydrogens. We have one here and one here, so the integral is 2. And the same goes for C. The reason that these 2 protons are the same label is because of the symmetry of the molecule. This symmetry allows these protons to be the same distance away from every single part of the molecule. Therefore, they occupy the same chemical environment. Therefore, we have 2 label Bs and 2 label Cs. Next, let's count how many label Ds we have. We have 1, 2, 3, 4, 5, 6, so the integral is 6. The reason these protons are the same label is because single bond rotation allows them to rotate and occupy the same space. So, the integral of label D is 6. Now let's look at label E. There is one label E, and so the integral is 1. And the same goes for F and G. The reason F and G are different labels is because it is on a double bond, which cannot rotate, and therefore they are locked into chemically distinct environments. Now let's take a look at multiplicity, or how many neighboring protons there are. A neighboring proton is considered a proton that is 3 or fewer bonds away from another proton. So remember, 3 or fewer bonds away. You might remember something called the n+1 rule. The n+1 rule tells us the shape of the peak, where n is the number of neighbors. So for example, if a proton has 1 neighbor, n equals 1, so 1 plus 1 is equal to 2, and the peak shape will be called a doublet. If a proton has 2 neighbors, we say n is equal to 2, and so 2 plus 1 is equal to 3, and the peak shape will be a triplet. What I mean by this is a singlet, S, will look something like this, a doublet like this, a triplet like this, and so on and so forth. Let's see how that works in this example. So label A has 0 neighbors. Therefore, 0 plus 1 is equal to 1, and we have a singlet. the multiplicity of label A is a singlet, and we denote that with an S. Label B has one neighbor because if we count the bonds from the label B hydrogen, we have 1, 2, 3. Hydrogen C as a neighbor. When we do n plus 1, we get 1 plus 1 equals 2, so label B is a doublet. And we denote that with a D. Same thing for label C. Label D has 0 neighbors, so it is also a singlet. Again, we can count the bonds, so start at a hydrogen, 1, 2, 3, and it cannot reach any neighboring protons, so there are 0 neighbors. Label E is a bit more complicated. Proton E is within 3 bonds away from proton F, 1, 2, 3, but it is also 3 bonds or fewer away from proton G, 1, 2, 3. Therefore, it has 2 distinct neighbors. And when we have 2 distinct neighbors, we need to do the n plus 1 rule twice. So, since there's 1 proton F, the n plus 1 rule would make that a doublet. And since there's 1 proton G, the n plus 1 rule would also make that a doublet. And together, we get a DD, or doublets of doublets, for the multiplicity of proton E. So we write that down in shorthand as DD. Sorry, that's my cat. And if you have time, I would encourage you to pause this video here and try to determine the multiplicity labels for F and G. Hopefully you had some time to try that out. If we catalog the neighbors for proton F, you see that it is neighbors to 1 proton G and 1 proton F. Therefore, proton F is also a doublet of doublets. Do the same thing with proton G, and you should get that it is also a doublet of doublets. Finally, we have chemical shift. When determining the chemical shift in Chem 3B, you will refer to this chart. You will take a look at what type of carbon the hydrogen is attached to, and then you will also look at what R group that carbon is attached to. So for proton A, we have a hydrogen attached to an sp3 carbon, and this sp3 carbon is attached to an R group, which is an oxygen. Let's take a look at the chart. That corresponds to this chemical shift right here. A hydrogen bonded to an sp3 carbon, bonded to an R group, which is an oxygen. So our ppm should be about 4. And we're going to write that in our chart. Let's try another one. Proton C is on an sp2 carbon, and that sp2 carbon is part of a benzene ring. If we look at our chart, that corresponds to this. A hydrogen connected to an sp2 carbon, which is part of an aromatic ring. And because of that, we say that the chemical shift is going to be between 6 to 8 ppm. And we can record that again in our chart. Go ahead and pause this video to try the rest, and then we'll cut to the answers. Now that this table is filled out, we have enough information to determine which protons the signals correspond to. Let's take a look at the NMR spectrum. Starting at the left here, we see that there are 2 doublets in the 6 to 8 ppm range, which correspond to label B and C in this chart. To distinguish them, notice that proton B is closer to the electronegative oxygen than proton C is. Because of that, proton B is more deshielded, and so it will have a higher ppm. Thus, we can say that this label is B and this label is C. Next, we have these 3 doublet of doublets, which must correspond to E, F, and G. To distinguish them, we can again look at the chemical shift. This doublet of doublet has a higher ppm than these two, and that must be label E because it is closer to the electronegative atom. So we're going to label this E, and we can group these two as F and G. Next, we have 3 singlets in the NMR spectrum, and if we look to our table, an integral of 3 with a multiplicity of a singlet, that must be label A. And finally, we have an integral of 6 with a multiplicity of a singlet, and if we look at the chart, that must be label D. And that's it for proton NMR. Hopefully that felt a little bit less daunting. If there's anything to take away from this, it's these 4 things right here. Remember to look at the labels, the integrals, the chemical shift, and multiplicity when trying to analyze an NMR spectrum. Before moving on to carbon NMR though, I want to note that you should be careful when determining the labels for your protons. Some protons that may appear equivalent are actually chemically distinct, and we call them diastereotopic protons. So to understand that, I want to start with this molecule. In this molecule, these protons in blue are chemically equivalent. But why is that? You might recall something called a replacement test. In this test, you replace H wedge with some arbitrary R group. In this case, we're going to use a smiley face because it's cute. So H wedge gets replaced with smiley face. And then you do the same thing for H dash. So you're going to replace H dash with smiley face. Then what you're going to do is you're going to analyze the stereochemical relationship between these 2 molecules. If they are enantiomers, the protons are the same labels, and if they're diastereomers, the protons get different labels. As you can see, these 2 molecules are mirrors of each other. If you imagine mirroring in the front, you will get exactly this molecule. Therefore, they are enantiomers, and these protons are chemically the same. Here's an example of diastereotopic protons. So we're going to do the same thing, where we replace H dash with smiley face. Oops. Boom. And H wedge with a smiley face. Then we're going to look at the stereochemical relationship between these 2. You're going to find that you cannot mirror this molecule to get this molecule. They will never be the same. I'll show you an example. If we imagine a mirror in the front of this molecule, you're going to get something like this. The bromine group becomes dashed, and so it is different from this molecule. This molecule can never become this, therefore they are diastereomers, and these protons are chemically distinct. So if we were to label them, for example, I would say this is HA and this is HB, but if I were to label these protons up here, I can label them as the same thing. So to summarize the replacement test, you're going to replace H wedge and H dash, each with some arbitrary R group. And then you're going to compare the resulting 2 compounds, and you're going to look at the stereochemical relationship. So if they're enantiomers, then the protons will get the same label. But if they're diastereomers, the protons get different labels. Finally, we have carbon NMRs. Generally in carbon NMR, at least for most of the ones you'll see in this course, the signals show up as singlets, so we don't really worry too much about multiplicity. So the 3 big aspects here are labels, integrals, and chemical shift. Labels work the same way, just this time you're labeling carbons and not hydrogens, and the integrals also work the same way. The only real difference here is the chemical shift. Chemical shift depends on the hybridization of the carbon and what R group it is attached to. We have this chart to look at to determine the chemical shift of the carbons. So for example, carbon B is an sp2 carbon of a carbonyl. As a reminder, a carbonyl is a carbon double bonded to an oxygen. And if we go back down to the chart, an sp2 carbon of a carbonyl will be between 150 to 220 ppm. Again, taking a look at the spectrum, the carbon B signal is indeed between 150 and 220 ppm. If we take a look at carbon C is an sp3 carbon attached to an electronegative atom, an oxygen. Taking a look at the chart, an sp3 carbon attached to an electronegative atom belongs in the 0 to 80 ppm range, which is consistent with what we see in this chart. There's also some other rules that are generally but not always true, and they might help you distinguish signals for carbon NMRs in this course, but in real experiments, it might not be as straightforward. So these are generally true, but not absolutely true. So integrals can correspond to peak height. So generally, the greater the integral, the taller the peak. And for hydrogens, the more hydrogens that are attached to a carbon, the taller the signal. So 0 to 1 hydrogens usually correspond to a shorter signal, whereas 2 to 3 hydrogens usually correspond to a taller signal. But please note that this is not always true, but it may help you sometimes in distinguishing peaks. That's it for this NMR review video. If you guys have any questions, I'd be happy to answer on email or office hours or ed discussion. And happy NMRing!